Welcome to the next video in the mathematical logic sequence talking about propositional logic, and in this video, truth tables and normal forms. As you can see on the whiteboard, I've drawn a fairly standard truth table that you've likely seen before. And the point that I want to make here is that truth tables are effectively functions from what is like a truth value assignment here over to the truth value that the sentence takes on this truth value assignment. So from this perspective, truth tables are basically like maps from really atomic truth value assignments to some truth value, true or false. Now, that's not quite the whole story because, of course, just specifying the truth value on a finite collection of atoms is not a full truth value assignment or an atomic truth value assignment, since those make assignments to every single atom. So this is more like a mapping from a finite portion of a truth value assignment to a truth value. But we will still regard the truth table in the way that I have now on the slide as a mapping from atomic truth value assignments to the set TF. And I want to point out that the book actually doesn't make it atomic truth value assignments. I chose to go with atomic truth value assignments because that just looks more like what we're familiar with in a truth table. But it actually doesn't matter whether you take this to have as its domain the atomic truth value assignments or the truth value assignments generally. So in any case, to kind of put the pieces together here, if we fix a sentence phi, and in this example this would be like our phi, we can determine the truth table for that phi, and we will call it E sub phi. That will be a function with its domain, the set of all atomic truth value assignments, and its range, the set TF. And when I give this function a particular atomic truth value assignment, what will it return? Well, we want it to return the truth value that the sentence gets for this truth value assignment, or the atomic truth value assignment. So we take V0, the atomic truth value assignment. Technically, we have to extend it to all of V to then evaluate phi on V. Those are some technical details, but the important point is that we basically find the truth value of phi on this truth value assignment to the atoms. And that is the definition of E sub phi, which is to say that is the truth table. Okay, so sentences are equivalent, right? So we're going to basically just practice this concept a little bit just by noticing that sentences are equivalent if and only if they have the same truth table. So that is to say, suppose we have some two sentences, phi and psi, and that they are equivalent to each other. We are then going to prove that they have the same truth table, and then later on in the proof we're going to go in the other direction. But for now, we assume that phi and psi are equivalent. And then we want to take any, or we want to prove the equality of their truth tables. And what that means is that we need to take any input and show that it has the same output for the two different truth tables. So effectively what that means is that we want to show E sub phi on this arbitrarily chosen atomic truth value assignment is the same thing as E sub psi on the same input. So how do we do that? Well, okay, what is E sub phi on this truth value, atomic truth value assignment? It is what you get when you take it and extend it to a full truth value assignment and then find the value of phi on that. Well, by our assumption that they are equivalent, then you would get the same value for this V on input psi. That's just the very meaning of equivalence of sentences, is that all truth value assignments assign them the same truth values. And then that, by definition of E sub psi, is this thing over here, E sub psi on the atomic truth value assignment. And so we are done with this direction. We can then go to the converse. So for the converse, we're going to assume the equality of the two truth tables and then prove that they must be equivalent to each other. To prove that they're equivalent to each other, we need to consider any arbitrary truth value assignment, V, and we need to argue that the value that it gives phi is the same as the value it gives psi. We can, in particular, get down, right, we do need to talk about some inputs to truth tables, right? If we're going to talk about the equality of these two functions and use that somehow, we're going to want inputs to the function, and so we need an atomic truth value assignment. So if we just take the atomic sentences that occur in either phi or psi, then we can consider the any atomic truth value assignment which agrees with V on those atoms, right? So that's what this V sub naught is that we construct here, is we effectively just restrict to the sentence letters that are in either phi or psi, and look at it, look at the atomic truth value assignment that assigns the same values to those atoms. And then we can look at plugging this thing into our truth table. E on that input must equal, E sub phi on that input must equal E sub psi on that same input, because after all, they are the same function. But by definition, E sub phi gives us V of phi. E sub psi gives us V of psi. And so we're done, right? We have proved that phi and psi are equivalent. Okay, so to carry on to talk about semantic completeness, I'm going to define this somewhat roughly as something to do with finite truth tables, right? Because as we've kind of mentioned before, truth value assignments are assignments to an infinite collection of atoms. And when dealing with truth tables, we want to focus only on finite segments. And that kind of goes hand in hand with the fact that our sentences are always themselves finite, right? So, so we do need to be sort of restricting our conversation here to finite truth tables, so to speak, which is to say just assignments to a finite collection of atoms, right? Truth value assignments to a finite collection of atoms, namely those that occur in a sentence. So what you could imagine, in order to help kind of understand what we mean by completeness here, is you could imagine writing down the table. So imagine you wrote down the table, which is to say, you've got T, 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 and we maybe map that over to F, right? I'm making up an arbitrary table. So then you could have T, T, F and map that over to T, and then T, F, T, and map that over to T, and so on. And, this thing may go on as long as it needs to go to fully specify all of the possibilities for the assignments to the atoms. And as you go, you assign each one a truth value. And then the question is, does there exist a sentence in our set of sentences which has that as its truth table? If it does, then we call the set of sentences semantically complete, because this is all we want for the semantics of propositional logic, is just to capture these truth value assignments. And so if every assignment has some sentence that effectively expresses it, then it's semantically complete. And I'm going to leave this description, so I'm just going to leave it at that, and also, I guess I'll also state that our set of sentences is semantically complete, and we will see in a moment how to demonstrate. But I'm going to, rather than try to formalize this too much, I'm going to leave it at this somewhat intuitive description, because I think the way that our semantics here and the progression of the textbook hasn't made it especially easy to talk about this in a fully rigorous way. I think I would have somewhat redesigned this if I were going to sort of build it myself, so that this whole conversation would have come out more easily. So for now, I'm going to just leave it at this rough description and hope that it doesn't cause any sort of downstream difficulties. Here's an introduction to disjunctive normal form. I'm going to start just by showing you something that's in disjunctive normal form, this thing right here. So it's in disjunctive normal form because it is made up of a bunch of disjuncts, right? It is a disjunction pretty much all the way through, so to speak, at least as like the main connective is concerned. So what I want, well, I'll say more about that in a minute. But in any case, then also what you need for disjunctive normal form is that each disjunct is a conjunction. That is necessary, right? So this is a conjunction, this is a conjunction. So that's also something that you need for this thing to be in disjunctive normal form. And then finally, the conjunction is made up of conjuncts which are negatomics. And negatomics are sentences that are either atomic or negated atomic sentences. So to put it briefly, disjunctive normal form is a disjunction of conjunctions of negatomics. I want to point out that you can have many different equivalent sentences that are each in different disjunctive normal forms, right? So this sentence that we started with, P1 conjunction, P2 disjunction, blah, 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 right? That is actually equivalent to just the sentence P2, and technically P2 is in disjunctive normal form. Now, how it doesn't maybe look like it based on everything that I've said, but technically it counts because we allow disjunctions of one disjunct, right? So that's like an edge case, but we allow it. So if you imagine, this is a disjunction with two disjuncts, well, we can, in a somewhat sort of similar way, regard that as a disjunction with one disjunct. And likewise, that disjunct, the one disjunct that is here, is itself a conjunction where it's a conjunction of length 1 again, right? So by the same sort of idea, we regard it as a disjunction of a single negatomic, and it is a negatomic because P2 is a negatomic, right? So the next thing that I want to point out is that the disjunctive normal form, right? Every sentence has an equivalent sentence which is in disjunctive normal form. So we often talk about finding the disjunctive normal form of a sentence, right? Which is to say, find another sentence which is equivalent to it and is in disjunctive normal form. So let's go back to this sentence that we already have the truth table for, this negation P1 conjunction P2 arrow P3, and let's find its disjunctive normal form. And I want to use this one because we're going to use the truth table to get the disjunctive normal form, or at least one of its, right? As we've said, there's no unique disjunctive normal form, so we're going to get some disjunctive normal form for this sentence. Basically, the way that you do this from the truth table is you consider only the rows at which the sentence is true, right? So everywhere that the sentence is true, you select those, and for each one, we're going to write down a conjunction of negatomics. So in the first row, I'm going to write down P1 conjunction P2 conjunction P3. And in the next row, I'm going to write down P1 conjunction P2 conjunction negation P3. And then I think you probably see the pattern by now, P1 conjunction negation P2 conjunction P3. And so on. So for every one of the rows at which the sentence was originally true in its truth table, right? You select those rows, you look over to the assignments to the atoms, and wherever the assignment was true, you write down the atom, and wherever it was false, you write down its negated atom, and you conjoin them all together. And that's how you get the conjunctions row by row. And then the disjunctive normal form is just going to be the disjunction of each one of these. Here, sorry, I see that is in the way, so probably doesn't Probably is already clear what is under there, but here I'll just move this. Okay. So that's how you can find the disjunctive normal form for any given sentence. And I just want to give a brief moment to talk about, like, making sense of this, I guess. What this effectively says, right, is it says, I am going to, right, this conjunction says I require that P1 and P2 and P3 are all true, just like in this row. And if that is so, then I give the sentence truth, right? So just like, well, anyway. And the fact that we disjoin that means, okay, that's one row at which it could be true, but we say, or maybe we're at this row, in which case P1 is true, P2 is true, and P3 is false, because that then means that this negated atomic evaluates to true, and then the whole sentence will evaluate to true. So that, in a sense, this is just kind of a one-to-one reading off of what the truth table is telling us, that, like, this is basically enforcing this scenario, and then by taking the disjunction of it, we're saying, okay, in this scenario, we get truth, or if we're in this scenario, we also get truth, or so on, right? So that's kind of the logic of the disjunctive normal form and why it works. Okay, and before moving on, I just want to finally state what disjunctive normal form is, or at least show it in the more technical way of writing it. So something is in disjunctive normal form if it is of this form, right? So that's a bunch of sentences, right? Each phi sub I is going to be a sentence, and we're taking the disjunction of some set of sentences, right? So that's the first level of description of what disjunctive form must look like to qualify as disjunctive normal form. But also we impose the condition on each phi sub I, of course I ranging from 0 to n, that each one of them must be of the form psi sub some subscript, right? I mean, I'm just, for technical reasons, I'm giving these subscripts further subscripts, but I don't necessarily want to sort of like get into why it has to be that way, just to kind of give myself enough subscripting that I can possibly take different sentences at every point. But in any case, so the important point is that each phi sub I must be a conjunction of some number of sentences. And then each one of those conjuncts, which is to say each phi sub I sub k, right, which is just any one of these things that occurs as a conjunct, must itself be a negatomic, which is to say that it is some atomic sentence or the negation of some atomic sentence. So there is the more technical description of the disjunctive normal form. Okay, just as there is a disjunctive normal form, there is also a conjunctive normal form. And to get, right, so the description, first of all, is that it will be a conjunction of disjunctions of negatomics, right? So in a sense, kind of the conjunction and the disjunction are swapping roles. Now, how do you get the conjunctive normal form for a given sentence? We saw before how we can get the disjunctive normal form by reading off the rows at which the sentence is true. We could also read off, right, to get the conjunctive normal form, here's the plan. We will read off the rows at which the sentence is false. Now, what that's going to do, and we basically get the disjunctive normal form for the rows at which it is false. We don't stop there, so don't be too confused, right? What that effectively gets us is the disjunctive normal form of the negation of the sentence, right? So, like in this example, if I were to read off the rows at which the sentence is false, then I would start forming the following disjunctive normal form. So I've only written down the first couple of disjuncts, but I'm taking them, of course, from the rows at which the sentence is false, right? And so since I'm taking it at the rows where the sentence is false, I am effectively getting the disjunctive normal form of the negation of my given sentence, right? And so if I take the negation of this, right, the two negations cancel and I get a sentence equivalent to phi, my original sentence. So the idea here is that we take the negation of this disjunctive normal form, right? If you take the negation of the disjunctive normal form and push that negation through the disjunction, right? Use your distribution laws to push the negation over the disjunction and then push that negation over the underlying conjunction. It's going, right? And then, maybe cancel double negations on the negatomics or whatever to get negatomics. That's going to put this sentence into conjunctive normal form, and it will be equivalent to phi. So that's how you can get the conjunctive normal form for a sentence. Is, again, you look at the truth table, you identify the rows at which it is false, you write down the disjunctive normal form for those rows, and then you put a negation on the whole thing and push it through. That gets you the conjunctive normal form.